in the last lecture, we introduced the concept of Minkowski spacetime, which is characterized by the following line element: a square minus c square d square again. This is the spatial part, this is the temporal part. Now, this captures separation between events and also contains the information whether the two events are causally connected or not, which we will investigate in this lecture in detail. So the first thing that we'll discuss is the time-like separated event. In fact, there will be three distinct notions of distance, which we will discuss one by one, starting from this time-like case. So let's consider a point particle of mass m moving in a trajectory, and that is a time-like trajectory. And if you consider 2 points which is close to each other, then we can write down the corresponding distance element in the following way: c square d square, and as the particle is moving with a velocity v, which is uniform, you can write d square. So if we simplify it, we give the following: c square minus square dt. Now we are viewing this particle from the lab frame S, and the time-like separated means d square less than. Now we can show that for time-like separated event, there always exists a reference frame, let's say frame S prime, in which dx prime be 0, and we call the corresponding dt prime as deta. That is, two events occur at the same location of space, but at two different points of time. Now for this case, we can also write down d square as c square d tau square. But remember that this is a Lorentz invariant quantity, so we can equate these two, which gives the following: d square and c square square, and this is again for our case this. Now from here we can see that d tau dt by gamma. Remember, gamma is 1 by square root of 1 minus c square by c square. And what is this tau? This tau is known as the proper time. Defined in a frame where dx, that is the spatial separation, is 0. And from this expression, you can see that as gamma is always greater than 1, gives the time dilation. Remember that you have seen from your undergraduate spectral course that moving clocks always tick slower. Okay. Now, one important point regarding this time-like separated event is the following: that they possess an frame invariant notion of time order. That is to say, for time-like separated events, time ordering between two events is Lorentz invariant. So you can faithfully describe what is the cause, what is the effect, because time ordering does not get changed if you change the frame, that you go from one inertial reference frame to other inertial reference. Please try to prove this statement. This is very important, and we leave that as an exercise for you. Also, we can draw the locus of all the points, let's say, from origin O, separated by time like distance, let's say alpha. So let's try to draw it. So let's try to draw it in 2D. So this is our CT axis or not axis, and let's say consider the one of the spatial axis x. So uh, we have the following equation for such trajectories of or locus of the time-like separated point from the origin. Let's say they are all these points are located at the same distance, some alpha. So x 0 c square is equal to minus alpha square, because the distance has to be negative. So we write it as minus times alpha square. It is explicitly negative. And this gives the following ct square square. Now, if you try to draw it in plane, it will give these two curves. And if you try to draw this for higher dimension, that is add more spatial axis y and z, we will see that locus of all the point equidistant from the origin and time like separated, nothing but a double sheeted hyperbola. So try to plot them and visualize by yourself. Now we go to the next case, that is we discuss the space-like separated event. Yes. Now again, let's write down the Minkowski line element c square. So because of this negative sign, as we know that it can be the ds square can be either negative, positive, or zero. Negative, if this is negative, we have discussed just now. That is the time like case. Now we discuss the case when it is actually greater than 0 because space-like separate. Separate. Why? So you can always go to a frame, let's say f prime, where you can set dt equal to 0 such that the events occur simultaneously, but dx is non-zero. Why you can do that? So if you look at it in f prime frame, dx square, the invariant distance, this is positive, and it is nothing but dx prime square. It is positive. Okay. Compare these to the case with the time like one. Compare these with the time like case where you can always choose a frame where you can set dx prime to 0, but dt prime not equal to 0. Why? Because again, this is negative, ds for negative for time like case. And so you can always do that because this is c square dt square with a minus. Okay. So keep this comparison mind. Now, he says the following that unlike the time-like case, there is no frame invariant notion of time order. That is, for two space-like separated events, you can go to another inertial frame where you can reverse the time order. So there is no notion of cause and effect for time-like space-like separated events. But what it gives is the following that in the s prime frame, you can say dt prime to 0, then this dx prime square is known as the square of the proper distance. Square. So let's again do this following exercise. So we know ds square is invariant. So we have minus c square plus dx, and that should be equal to dx prime. And if you rearrange this, you can see the following that dx prime square is equal to plus c square. So I've just rearranged this equation by taking this other side. Now you can see that among all the inertial frame, if you go to this particular prime frame where dt prime is 0, then this distance square, which is known as square of the proper distance, actually minima. And this reflects the fact that you have a length conversion. Okay. Now we look into the third case, which is the null or like separated. Before that, let us give you an exercise to do. So just like the timeline case, you should also try to find out the locus of all the points which are space-like separated, let's say from our origin, and try to draw them. Okay. What will happen? So you should get something like this. So if again this is your axis, this is your, let's say this is a x-axis, we have this. So in general, you will get a single sheeted hyperbola of revolution as a locus. So try to plot it and visualize. So for the null or like separated, dA square is basically 0, which means that if you solve this equation, this will mean that square. This is the trajectory followed by the light rays. So any two events, distance between them, distance means the sense of Minkowski line element is basically 0. Then they can be reached, they are connected by the light signal. And also one important thing that follows from here, you can see that you cannot set dx to 0. If you try to do that, dt will automatically, you get some trigger, which implies that you can never go to a frame which is the rest frame. For example, there is no rest frame of 4. So now this equation gives the following thing, and from here we can see that they give a double cone of angle 45 degree. These are basically locus of the points which are like separated from the origin. So let's draw it. So these are the like separated points. Here you have a time like separated. Again, I should write the axis. This axis is x naught, t times t, and this axis is x. And for the space like separated regions. Like time like, and this. So remember that you could have chosen the origin here at any point of the space time. So each point will have its own light cone, and the events that are causally connected will remain always inside the line. Also try to show that for light case also there is a frame invariant notion of time over. So we'll stop here, and please refer to the lecture notes for more details. We'll carry forward our discussion in the next session. Thank you for this.